Continuing section 3.6, we'll now turn to finding horizontal asymptotes of a rational function. And here it's basically a different set of criteria that we want to look at versus what we did with vertical asymptotes. So horizontal asymptotes are dealt with quite differently than vertical asymptotes. Given the rational function f of x equals n of x over d of x, where the polynomial in the numerator n of x has degree n, and the polynomial d of x in the denominator has degree m. If the degree of the numerator is less than that of the denominator, if n is less than m, then the equation y equals 0, the line y equals 0, which is the x-axis, will be the horizontal asymptote of the graph of the function f. If the degrees are the same, if n equals m, then the equation of the horizontal asymptote will be of the form y equals the ratio of the leading coefficients, that is a sub n over b sub m. Those would be the leading coefficients of the polynomials in the numerator and denominator. Y equals the ratio of the leading coefficients will be the horizontal asymptote of the graph of f. Finally, if the degree of the numerator is greater than that of the denominator, then the graph of f will have no horizontal asymptote. So there are three possibilities depending on the relative size of the degree of the numerator and the degree of the denominator. If the function has a horizontal asymptote, if a rational function has a horizontal asymptote, it will have no more than one. It will either have none or one. A rational function cannot have more than one horizontal asymptote. Let's apply these criteria now to the examples we looked at in example 1, the same functions, now with our attention focused on finding horizontal asymptotes. What we want to do with these is, rather than look at the zeros of the denominator, we want to compare degrees. So we need to know the degree of the numerator and the degree of the denominator. If we take our first example, f of x equals x plus 1 over x times x minus 1, and we multiply out the denominator, we can write it as x squared minus x. And just for emphasis, let me write the numerator as x to the first plus 1. So what we see here is the degree of the numerator is 1. The degree of the denominator is 2. So the degree of the numerator is less than that of the denominator. When that occurs, the horizontal asymptote, let me just abbreviate that as HA, the horizontal asymptote will be the line given by y equals 0. Or we can describe it as the x-axis. So the degree of the numerator is less than that of the denominator. Therefore, the x-axis, or y equals 0, is the horizontal asymptote of the graph of this function. If we return again to our sheet of graphs and look at the graph of example 2a, which is the same as the graph of example 1a, we see that the x-axis is indeed acting as a horizontal asymptote. The graph gets closer and closer to the x-axis as x either takes on larger and larger positive values or larger and larger negative values. Notice, by the way, that the graph actually crosses the horizontal asymptote at x equals negative 1 before it starts to return to getting closer and closer to the asymptote as you go further and further to the left. So while it's impossible for a graph to cross a vertical asymptote, it can cross a horizontal asymptote, and that's exactly what happens with this particular example. Next, looking at example 2, part B. G of x equals x squared over x squared minus 4. It's pretty clear here the degrees of the numerator and denominator are identical. The degree of the numerator equals the degree of the denominator, which is 2. So if the degrees are the same, we look at the ratio of the leading coefficients of the polynomials in the numerator and denominator. Those leading coefficients for both of the polynomials, each of those is 1, then the horizontal asymptote will be determined by the ratio of those leading coefficients. Y equals 1 over 1. That is, y equals 1 would be the equation of the horizontal asymptote of the graph of G. We now look at the graph of example 2, part B. You can see the line y equals 1 is shown here, this horizontal line, and that's the horizontal asymptote. You can see that as the graph goes to the left or to the right, that those pieces of the graph are getting closer and closer to that horizontal line. Our next example, part C, h of x equals 2x squared over x squared plus 4. Here again, just as in the previous example, the degree of the numerator equals the degree of the denominator, both of which are 2. If we then look at the ratio of the leading coefficients, which is what we have to do if the degrees are the same, then we see the ratio is 2 over 1 or 2. So the horizontal asymptote would be the equation y equals 2 over 1, or y equals 2. Notice, by the way, when we write the equation of the horizontal asymptote, we should always write it in the form y equals whatever value we've obtained. The only time you don't have to do this is if you describe the horizontal asymptote as being the x-axis. But if you even write the equation of the x-axis, you have to use y equals 0. So make sure you include the variable y when you write the equation of a horizontal asymptote. So now if we look at the graph, for example 2c, you do see y equals 2 is the equation of the horizontal asymptote, and you can see that the graph, as it goes to the right and to the left, is getting closer and closer to that horizontal line, flattening out as it goes in both directions. Now looking at example 2, part D, s of x equals x squared minus 4 over x minus 2. Again, we compare the degree of the numerator to that of the denominator. Here the degree of the numerator is 2, which is greater than the degree of the denominator, which is 1. When the degree of the numerator is greater than that of the denominator, then we will not obtain a horizontal asymptote. The graph will not have a horizontal asymptote in such a case. Essentially what this means is that the graph never flattens out as x gets bigger. The graph just either rises or falls, but does not flatten. It doesn't level off, that is, as x gets bigger or smaller. Remember that this is the function whose graph looks like a line with a hole in it. So let me show you that, and then we'll move on from there. Well, before I do that, I should at least say that the graph has no horizontal asymptote. Okay, so let me show you the graph now. So we see here the graph that we talked about previously is having no vertical asymptote. There's a hole in it at x equals 2. That hole is technically referred to as a discontinuity. And you can see that the graph does not level off. It doesn't have any sort of behavior that we would associate with a horizontal asymptote. So it just rises as it goes to the right and falls as it goes to the left and doesn't level off in any sense whatsoever, obviously being just basically like a straight line. We now turn to consideration of the third type of possible asymptote for a rational function. That's a slant or oblique asymptote. Given the rational function f of x equals n of x over d of x, if the degree of n of x is exactly 1 more than the degree of d of x, then by the division algorithm, f of x equals n of x over d of x can be written as q of x plus r of x over d of x, that is, as quotient plus remainder over divisor, where the quotient must be a linear function. It must have the form q of x equals mx plus b, that is, y equals mx plus b, because of the fact that the degree of the numerator is exactly 1 more than the denominator. The quotient will always be a first degree linear function. What this means is that as x gets very large or very small, either approaching positive infinity or negative infinity, in other words, as it gets large in magnitude, as its absolute value gets large, the fraction r of x over d of x, ratio over divisor that is, will get very small. It will approach 0. The arrow there is read as approaches. So r of x over d of x approaches 0. So as x gets large in magnitude, the function looks more and more like a linear function. F of x will be approximately the quotient, which is mx plus b. And the graph of f ends up looking like a straight line. This is what we saw in the example we were just looking at a moment ago, the line that has the hole in it. And we'll return to that example and see that we can consider that as a case of having a slant asymptote. So in such a case, we say that the graph of f has a slant or oblique asymptote. The graph is going to approach some kind of slanted straight line. The equation of the slant asymptote can be found by performing a long division, or in some cases, assuming you have the right kind of divisor, you can use synthetic division. In the very short amount of time I have remaining, let me just show you what's happening with this example we just looked at, example 2D. We have s of x equals x squared minus 4 over x minus 2. And what we saw is that by factoring the numerator and canceling the x minus 2's when x is not equal to 2, that s of x was approximately, well, I shouldn't even say approximately, it's exactly x plus 2 in this case, as long as x is not equal to 2. Well, the line y equals x plus 2 would be considered to be an asymptote of the graph. So essentially the graph is just following along this, just imagine the asymptote going right along here. It's just following along this slant asymptote and basically completely coincides with it everywhere except at x equals 2. So actually we don't even need to do a division to see that we have a slant asymptote in this case. Notice that the degree of the numerator is 1 greater than that of the denominator. The degree of the numerator is 2. The degree of the denominator is 1. In that case, we're going to get a slant asymptote. So this is an example, actually, of the occurrence of a slant asymptote.